Good morning everyone. In this module, we will discuss about descriptive mineralogy. A geologist considers minerals as the basic building blocks comprising nearly the entire crust of the earth. If geologists are to understand the earth, its formation and its dynamics, they must understand minerals. In the forthcoming lectures, you are also expected to learn mineralogy, structure, chemistry, optical and physical properties, mode of occurrences, and uses of the following group of minerals. They include olivine, garnet, epidote, aluminium silicates, pyroxene, amphiboles, mica, chlorite, feldspars, feldspathoids, and zeolites. Today, we are going to discuss some basics of chemistry related to the topics in mineral chemistry. This will help us to understand and discuss the mineral groups, their mineralogy, structure, chemistry, optical and physical properties, etc. in detail. To define a mineral is a naturally occurring crystalline solid with a definite but not necessarily fixed chemical composition. Minerals must be crystalline solids. The atoms or ions that comprise crystalline materials are arranged and chemically bonded in a regular and repetitive long-term pattern. All minerals have a definite chemical composition. A chemical formula may be written for any mineral. For example, the common mineral quartz having a chemical composition SiO2, which is composed of silicon and oxygen in a ratio of 1:2. The composition of many mineral species may vary within their certain limits. An example is the mineral olivine, which may be iron rich, which may be written as Fe2SiO4, or magnesium rich, which may be written as Mg2SiO4, or may have an intermediate composition. However, the proportions always work out so that the ratio of Fe plus Mg is to Si is to O remains 2:1:4. The nature of chemical elements in matter is composed of fundamental building blocks called elements that exist as discrete atoms and may combine to form molecules, crystals, and minerals. The atoms that comprise each of the elements are composed of the fundamental physical building blocks of matter, which are protons, neutrons, and electrons. In the Bohr model, electrons are like small spherical particles orbiting around the nucleus. Positively charged protons in the nucleus attract and hold on to the negatively charged electrons. The number of protons is called the atomic number. The outermost electrons in an atom are called valence electron. The valence electron strongly affect chemical properties. Elements which valence electrons is in similarly shaped orbitals are chemically similar. Atoms are more stable if electrons completely fill energy levels and sublevels. Atoms may give up or borrow electrons, becoming ions, to obtain this stability. Ions are atoms that have an excess or deficiency of electrons compared to the number of protons in the nucleus. As a result, they may become cations, which have a net positive charge because there are more protons than the electrons, or anions with a net negative charge because there are more electrons than protons. The ionic charge, are also called valence charge, is the number of protons less the number of electrons. We usually indicate valence by a superscript number after the elemental symbol. For example, Fe 2 plus indicates ion with 2 more protons than electrons. We call all ions with a charge of +1 or -1 as monovalent. Those with a charge of +2 or 2 minus are divalent. Trivalent and tetravalent refer to charges of +3 and +4. The process of losing an electron is called oxidation. Gaining an electron is called reduction. Oxidation leaves metal with a positive charge. They may combine with oxygen, which is O2 minus anions, to form oxides. Iron metal, which is Fe0, for example, may oxidize to become Fe2 plus or Fe3 plus. If Fe2 plus, which is a ferrous ion, combined with oxygen, it may form woostite. The composition of that is FeO. If Fe3 plus, which is a ferric ion, combined with oxygen, then it may form hematite. That is Fe2O3. Woostite and hematite are both minerals, but hematite is more common because under normal earth surface condition, iron easily oxidizes. Abundance of elements. Various attempts have been made to estimate the relative abundance of chemical elements in the crust. Of the 89 naturally occurring elements, only 8 are present in substantial amounts. These elements are oxygen, silica, aluminium, iron, calcium, sodium, potassium, and magnesium. These collectively comprise the large majority of the earth crust and are the elements from which most common minerals are composed. Determining the composition of the entire earth is even more difficult because the mantle and core cannot be sampled directly. Estimates are obtained by the earth's mass and density distribution as determined by geophysical means. Studying the composition of basaltic magmas derived from the mantle and the samples of the mantle that arrived with the magma. Analyzing the composition of meteorites that are presumed to represent the material from which the earth accreted, and applying cosmological, geochemical and petrophysical models to evaluate these data. As whole of the earth, the percentage of the common minerals in the crust includes 39% of plagioclase, 12% of alkali feldspars, 12% quartz, 11% pyroxene, followed by 5% of amphibole, 5% mica, 5% clay, and 3% other minerals. After this, you have about 8% non-silicates.